Hello folks, welcome to another session of the lecture series of magnetic field. So today we are just continuing on what we did last time. So last time we realized that when a charged particle moves in uniform magnetic field with angle 90 degrees, then the path will follow a circular path. So why circular? We realized that it's because the direction between the direction between that of velocity and this thing, the force, is always 90 degrees. So now our job today is to determine a formula for that force, and also find the radius of that circle. If it moves in a circular path, it should have radius, so we will find the radius. And if we can make the circle to repeat, the particle to undergo repeated circular motion within that magnetic field, then we can find the time period, the frequency, these sort of things. So, so that's our mission for today. So the first thing is expression for force felt by moving charged particle, in magnetic field, and that field is a uniform one. So it is a uniform magnetic field. So this is the title that we have today. So as I go on going through the content of last lecture, the diagram I drew was somewhat like this. This was the region where there was uniform magnetic field. So I drew a lot of crosses here, So let me draw only 4 of them here. The particle went like this. So it's a positive particle, and it felt the force. It went somewhat like this. So here the force was somewhat here. So let me draw the force by red color here. So this is the force. Maybe here this is the force. Maybe here this was the force, and so on. So this was the direction of the force. So now, in order to find a relation for that force, we have to know the factor on which it depends. So the first factor it depends on is this force depends on the magnetic field strength. It's because the moment of charged particle is equivalent to current, and if a magnetic field is high, then the magnetic field produced by this thing, and the magnetic field produced by the current, will interact more. So more interaction means more force. So again, F is proportional to charge. So if charge is more, that current is more, we can know that from the equation I equal to NQVA, the expression for the terminal velocity. So if charge is more, definitely current can be made more. If all other quantity is same, but if we make charge more, current is more. So when current is more magnetic field produced by the charges involving that current, and more interaction. So next, F is proportional to V. So again, if V is more, the current is more current means more interaction. And then another is F is proportional to sine of theta. So where theta is the angle between the directions of V and B. So right here we are doing like this to know the force. So it means that the angle between magnetic field and this thing, magnetic field is there, this thing is there, the angle is 90. But that is not always the case. Sometimes the angle might be like this. Sometimes it is not always 90. It might be like this. So this theta means this angle. So theta means this angle. So from that angle, it might be difficult to see this, but we can see this. You can see this. So this is the angle. So theta means that angle. So when you combine all of these things, I will have F is proportional to B into Q into V into sine of theta. When I combine all of them, it will be or F proportional to B Q V sine of theta, and we have a constant here, but we manipulate the unit system in such a way that we ultimately obtain F is equal to B Q V sine of theta. So this is the expression for the force, often called as Lorentz force for charged particles. Now, as we know from here, we can say that, we can easily conclude that if theta equal to 0 degree, I will have F is equal to BQV sine of 0, and that's equal to 0. That means if the charged particles are going right along the magnetic field, there is no force at all. So if theta equal to 90 degrees, F is equal to BQV sine 90, and that's equal to BQV, which is the maximum value. So this is minimum value and this is the maximum value. So this is the Lorentz force. As you can see here, this is a very perfect example of vector product. So if you have gone through vectors, and if you have dealt with topics like scalar product and vector products, this is a very good example of vector product. See, velocity is vector, B is vector, and we are getting force, and force is vector. So that's why this Q has just got magnitude, so it is just multiplication, and this is sine theta. So just like what we obtain in case of vector product. So if we have two vectors A and B, their vector product or cross product is equal to magnitude of A, magnitude of B, then sine theta, and to distinguish that it's a vector, we will have a unit vector somewhat like this. See, you can have Q is a magnitude, it's okay. So B vector, V vector, and then sine theta. So here we have written only magnitude, so that's why we don't need a unit vector here. So it's a very good example of a vector product. So vector and vector giving a vector. And this vector is always pointed perpendicular to the plane formed by these two vectors. This vector is always perpendicular to the plane formed by this thing. See, you can see here. So we have one vector, we have another vector. So this is the plane, and the force is here. So we have got one vector and one vector. So we have a plane, and this is perpendicular. So a very beautiful example of vector product. Now, with that, if I now want to find the radius of this circle, so what would that be? So let us say we make a charged body enter like this, and we see a curved path like this. We want to find the radius. So for that, what we have is the force, which we call as Lorentz force, is equal to BQV in this case, because here these things are perpendicular, that's why BQV. And since it moves in a circle, what you can say is this Lorentz force gives rise to the centripetal force. This Lorentz force has been utilized to create the centripetal force, and which moves the body in a circle. So that's why it creates this. So if it creates this, its numerical value should be equal. If it creates the other quantity, their numerical value should be equal. So I often have a healthy discussion with students in terms of this fact. So why should they be equal? They say, I give example as thus. I go to market, I give 2000 rupees and buy a pant. I buy the pant only if I feel that the worth of my money and the worth of that pant are equal. If I feel that they are not equal, I won't buy it. So that means the numerical value, the worth of the value of that pant and my money is equal. That's why I buy it. So that's why I buy. So that this is what we do. So their value, if something creates something, their numerical values are equal. So that's why this is this also and equal also. So this FL is BQV equal to this FC is mv square by r. So from here I can cancel something. This V and this V goes, which gives us or R is equal to mv by B and Q. R equal to mv by BQ. So the radius of the circle is given by the product of mass and velocity divided by the product of magnetic field strength and the amount of charge. So with that, what I can say is, therefore, R is proportional to mass. We'll discuss that. R proportional to V, R proportional to 1 by B, and R proportional to 1 by Q. So let's talk about that. So it says that higher the mass, more is the radius. That's true. It is true because, let's go for this thing. It was moving like this. If this thing is heavy, everything remaining same, and if this thing is heavy, turning it would be difficult. So that's why if it is heavy, then it will take more radius like this. So this is for heavy particle. This radius is for heavy particle. Heavy particle. So if it happens, R is more. And if it is light, this force can turn it like this. It can turn like this. So at that time, the radius is less. So heavier or more mass means more radius, and less mass means less radius. Next is velocity. If it is traveling slowly, this force can turn it very fast because it's weaker. If it is traveling fast, then turning it would be difficult. It's just like in the case of vehicles as well. Next is magnetic field. If we apply strong magnetic field, strong interaction, strong force, and it just rotates. If magnetic field is weaker, then turning is difficult. If no magnetic field, no turning. Same thing is charge also. If there is charge, there is current, and there is turning, like that. So that's why all of these things are related to radius in one way or the other. Now what we have is this mv. From our knowledge of dynamics, what we know that since mv is equal to small p, and small p is the linear momentum, that's why I must have this r can be written as p by bq as well. R equal to p by bq as well. Again, we can express this p in terms of kinetic energy. So what I can do is, also we know that since ke is equal to p square by twice m, you should know it. So if so, then I must have p square equal to twice m into ke, and this will give me, so let me rub it slowly. It's a very delicate setup I have, so I have to rub slowly. So I'll have this p is equal to root twice m into ke. So therefore r is equal to root of twice m into ke divided b and then q. So r has been expressed in terms of kinetic energy as well. So now we apply these conditions in certain questions like this. So we are told to, we are given a condition in which a proton and an alpha particle are entering the same magnetic field with same velocity. So then we are required to compare the radius. So one is proton and one is alpha particle entering the same magnetic field. We have to compare their radii. So radii p by radii alpha equal to what? So my question will be, radii for p should be equal to mass of proton into v by b into q of proton. So let's just leave it like this. mp is mp, v is okay, b into this is e, because charge of proton is equal to that fundamental charge e. Now radius by alpha is equal to mass of alpha into v divided b into q of alpha. That's equal to mass of alpha is 4 into mass of proton, then v, because it is what it is. Then we have got b here, b, and then this q alpha is 2e. So this 2 and 4 gives us 2. So this gives us equal to so let me do it here. Let's not to do it down. Sometimes I'll need to crop it. So equal to 2 mp into v by b into let us say e. So this thing is equal to the radius of proton. So therefore r alpha is equal to twice of rp, which means the ratio that we have is rp by r alpha will be equal to 1 by 2. So alpha will have more radius, heavier thing, and proton will have less radius. So this is the ratio. So in such cases, we can use this formula to solve the problem. Now, next is, here we have assumed that the charged particles have entered the magnetic field exactly with angle 90 degrees. What if the angle is not 90 degrees? So in that case, what I do is, so initially I had this condition. So what happening is, particles integrating like this, angle 90, and it moves in a circle. So it moves in a circle like this. If we move a full circle, it moves in a circle like this, full circle. And it goes on repeating. The magnetic field is there, the space is there, it is confined there, it just repeats. But what if this is not perpendicular? If it is like this. Now what happens is, this thing will move in a circle, it's okay. In addition to moving in a circle, it has to move up, because here it has got some upward velocity as well, upward velocity. Initially it was horizontal as well, now it is upward as well. So what happens is, it has to move upward as well as moving in a circle. So if something moves upward as well as in a circle, then this path will be spring-like, which is called as helical path. So helix or helical path, that's because of movement of this circle along the axis. Translation of this circle along the axis gives us helical path. So we have words as helix, we have words as helicopter, we have and so on. So in DNA, in human DNA, we have a helix type structure. There's a double-stranded helix type structure, somewhat like that. I studied during school days, and that often comes to my memory and often goes. So because I'm a physics person actually, so it must move in a helix. So when it moves in a helix, what happens is, so this velocity has got two velocities. One is a horizontal, one is vertical. This horizontal interacts with the magnetic field and gives Lorentz force. This horizontal velocity gives the Lorentz force, and it causes this thing, and this causes this thing. So this is the vertical velocity, this is the horizontal velocity. Each of them have got different jobs. So what is happening here now is, the movement in a circle is done by horizontal. So that's why here we should have, so let's write this thing first. If this angle is theta, we have got horizontal, in this case, let's write, so if theta is unequal to 90 degrees, the two components of velocities cause helical motion. So first we have to write, what we have to write is the component which is along the magnetic field. The component here along the magnetic field, so the component along the magnetic field, so we write it as a V parallel. V parallel means along the magnetic field. V parallel causes upward, causes movement of circle, movement of a circle along the perpendicular axis. And then this component, which means this component here, it is the component which is perpendicular to the magnetic field. So the component perpendicular to the magnetic field, so which write as V perpendicular. So this V perpendicular causes circular motion. So we will have, excuse me. So we have BQV sine theta is equal to BQ. Let's not write this. BQV perpendicular sine theta. Sorry, let's not write sine theta actually. Is equal to mv perpendicular square by r. by r. It is just this component. So this component is perpendicular to the magnetic field. So we write like this. So this and this cancel, which gives us r is equal to mv perpendicular by bq equal to mv sine theta by bq. This is the radius of the circle. So radius of the circle there. Now we have to find the if it is a helical, we have to find the pitch. We have to find the pitch of that circle. So that pitch requires the time period. So that pitch requires the time period. So that we will do in some other cases. So for here I can write it as, so r is equal to p sine theta by bq, linear momentum, or I can write it as I follow the previous case, twice m of ke then sine theta by this bq. So this gives the radius of the circle in this case, and this radius depends on theta. See here. So if theta is 0, radius is very less, so it just goes like this. That means very small radius. If theta is high, then it will take large radius, somewhat like this. So this is the calculation of radius if the angle is perpendicular, angle is 90 degrees, and if the angle is not 90 degrees. So here v parallel means the velocity along the magnetic field, and v perpendicular means the velocity perpendicular to the magnetic field. So let's take that into account and proceed likewise.